Let us look at example 3. In example 3, you are given two coils of wires. One is X and one is Y. For simplicity, I've drawn it in this view so it's easier to do my question. And you are asked to find the magnitude of the total magnetic flux density at the center of the coil. So this is what we want to find. B resultant, I'm going to call this resultant, at the center of the coil. Now we know that the magnetic flux density at the center is due to the magnetic flux due to X plus the magnetic flux that is due to Y. And we also know that B itself is a vector quantity. So whenever we want to sum two terms that are vectors, we need to sum them up. The summation must be vectorial. Alright? So we need to consider the direction of both X and Y. We know the current of X is in this direction. Okay? So the magnetic field due to X will actually, if you use your right-hand grip rule, you'll find that it's actually pointing out of the paper. We also know that the current due to Y is in this direction, and so we know that it also contributes a magnetic field. But now, if you use your right-hand grip rule, you realize it is out of the paper. I've drawn it a little away from each other so that you can see better. So this means both of them are in opposite direction. Hence B resultant, if I take coming out of the paper as positive, so let me write out of paper as positive direction, then what we will have is this is negative Bx plus By. The next concept we need to know is what is the magnitude of Bx. We know for a coil, the magnetic field is given by mu naught n I over 2r, where r is the radius of the coil. With that, then we can write in that this is equals to mu naught nx Ix over 2Rx negative plus mu naught Ny Iy over 2Ry. Substituting the values from the question, you can do that. You will be able to find that this is actually equals to 0 Tesla.